This is the first in a short video series about projection in linear algebra. Projection is super useful, with applications in fields like computer graphics and statistics. In fact, under the hood, linear regression is all about projection. But that's a topic for another day. This video will cover the properties of projection, while the next one will look at formulas for calculating projection matrices. Projection is sort of like taking a vector and then shining a light on it, and then seeing where its shadow lands on some space of interest. We might be interested in projecting on the coordinate axes, like in this example, but we could also project onto some other line, like this. As an example in higher dimensions, if we want to project this vector onto this plane here, we again shine the light and see where the shadow is. Though we could also project onto a line. Any lower dimensional subspace is fair game. In this video, we'll be considering orthogonal projections, meaning if we draw a line from our projected point to our original point, that line is perpendicular to the space we're projecting onto. Projection is intrinsically tied up with the dot product of vectors because of how the dot product works. You can think of the dot product as what you get if you project one vector in the direction of another and then multiply their lengths. Projection is a linear transformation, and so we can represent it as matrix vector multiplication. This means that if we start with a column vector, like this one here, then there's some projection matrix that you can multiply the vector on the left, and the result will be the projected column vector. If the starting vector is called x, then what we're doing is multiplying by some projection matrix that we'll call p to get the projected result that I'll call x hat. An alternative way to picture what the matrix is doing is that we can imagine starting with a vector in every point in space and seeing how they all get projected down, like this. In another video, we'll take a look at how to actually calculate these things, but this video is about the properties of these orthogonal projections. The first property is that doing the projection twice, or any number of times, is exactly the same as doing it once. Once we do the projection, then we're already living in the shadow world, so to speak, and so trying to perform the same transformation again has nowhere left to take us. To paraphrase George W. Bush, project me once, shame on you, but you can't get projected again. Algebraically, suppose we take some vector x and then project it by multiplying p times x, where p is our projector. If we try to project it again by multiplying p times x, giving p squared x, we'll find that this has not changed the result at all. Flipping this around to the way it's usually written, we can say that p squared x equals px, or more simply, that p squared equals p. There's a special term for matrices that have this property. We say that they are idempotent. And it's not just squared either. Doing the same projection any number of times is the same as doing it once. That property isn't so hard to understand. Another property that orthogonal projection matrices have is that they are symmetric, meaning P transpose equals P. This one is hard to understand, in part because it's hard to get a good handle on what the transpose of a matrix does visually in terms of linear transformations. I actually made another video all about the transpose, but here I want to explain this in a different way from that video. For our setup, pick any two vectors that I'll call u and v. We'll also pick a subspace to project both of them onto, like this plane. And then let's do that projection. Suppose we then take the dot product of the projected vectors. Would it surprise you to learn that we can get the exact same dot product result if we only project one of the vectors instead of both? For example, maybe we only project u onto the plane, but don't project down v. Taking the dot product of these two vectors is going to give the same exact number as if we projected both of them. We could also go the other way, dotting u with the projection of v. Projecting only one and taking the dot product gives the same result as projecting both and taking the dot product. I think that's unexpected. Let's look at it again in fewer dimensions. Now we're projecting the vectors u and v onto this line here. The claim again is that we'll get the same result if we project both vectors and then take the dot product, or if we only project one of them and then take the dot product with the other, and that we can pick either one. And why? Well, the reason is because of what we said earlier about dot products. It's what you get if you project one vector onto the other, then multiply their lengths. So as long as one of the vectors is projected, then the dot product will automatically project the other one. But let's do a little proof. First, break both of these vectors into the sum of two parts. One is the projection, which lives on the surface we're projecting onto, and the other part is perpendicular to that surface, which is sometimes called the rejection, by the way, and I'll label it with this perpendicular symbol. What's key here is that the dot product distributes over vector addition. If we were to take the dot product between the projection of u and the original v, like this, we can decompose v as this sum, and then distribute the dot product over the sum. The first term is just the dot product of both projected vectors, but the second term has to be 0. One of these lies on the line, and the other is perpendicular to the line, so their dot product is 0. And you can go the other way as well. If we dot u with the projection of v, we can expand u, then distribute the product. Dotting a projection with a perpendicular gives 0, and so all three of these must be equal to each other. So it doesn't matter whether we do the projection on the first vector or on the second or to both, we still get the same dot product. Now let's take these dot product equations and write them in their equivalent matrix multiplication form as the transpose of the first vector times the second. When we project the first vector, we have to distribute the transpose onto the projection matrix too. Since these two expressions are equal to each other no matter what u and v are, that implies that p transpose must be equal to p. So the way I'm thinking about all this is that p transpose equals p is just the math telling you that you can project either the left vector or the right vector and still get the same dot product. So this all just represents that the transpose, the dot product, and orthogonal projection are all intrinsically tied up together. The next property of orthogonal projection matrices I want to look at is that projecting always reduces the number of dimensions we're living in, isolating us to a smaller subspace of the space we started in. Intuitively, you can think that when we make shadows in real life, the original objects are 3D, but the shadows live on a 2D surface, like the ground. What that means for us in practice is that the matrix has less than full rank. Recall that the rank of a matrix tells you how many dimensions its output spans. If the matrix is less than full rank, that means there are some directions that the matrix transformation sends to 0. For example, consider the orthogonal projection of the 2D plane down onto this line. Now consider vectors that originally lie on this other line here that's perpendicular to the line we're projecting onto. Any vector that lies on this line will get sent to 0 when we do the projection. This line is therefore called the null space of the transformation. The outputs of this projection all live on this one-dimensional line, and so we'd say P here is a rank 1 matrix. On the other hand, when we projected onto a plane earlier, that would be a rank 2 transformation, since planes are 2-dimensional. This is also related to eigenvalues, which brings us to our next property. The eigenvalues of projection matrices are all 0s or 1s. I'm assuming that you have a good geometric understanding of eigenvalues. If not, pause here and go check out the video on this topic by 3 Blue 1 Brown.
So why are the eigenvalues 0 or 1?
Let's actually ask instead, where are the eigenvalues 0 or 1? Meaning, which eigenvectors have these eigenvalues? When we do this projection, which vectors end up still pointing in the same direction after the transformation? Most vectors, like say this one here, will be pointing in a different direction after the transformation, and so will not be eigenvectors. But there are two sets of exceptions. Start with the surface we're projecting onto. Vectors on this surface, like this one here, are already projected, so they don't change with the projection, which means they're still pointing in the same direction before and after. Another way to say that is that all the transformation does is multiply these vectors by 1, which is exactly what it means to have an eigenvalue of 1. Next, go back to the null space. Any vector in the null space is going to get sent to 0 by the transformation. But that's the same as just multiplying the original vector by 0, which is what it means to have an eigenvalue of 0. So to recap that, projections have eigenvalues of 1, which correspond to eigenvectors on the surface we're projecting onto, and eigenvalues of 0, which correspond to vectors in the null space. For our next few properties, let's look at combining projections in two ways. First, we'll find that orthogonal, nested, and orthogonally overlapping projections commute. By commuting, we're talking about doing one projection after another. First project onto one subspace, then project the result down onto another subspace, which we can also write as two successive matrix multiplications. If the two projections commute, that means we could do the two projections in either order and still get the same result either way. Just like how matrix multiplication in general does not necessarily commute, projections do not necessarily commute. But the reason we care when they do is because it turns out that if two projections commute, then their combination will also itself be a projection. The simplest case where projection matrices commute is when they project onto orthogonal subspaces. The reason they commute is because either way you just get 0. For example, suppose we project first onto the x-axis, and then project the result onto the y-axis. Projecting onto x kills the y component, so there's nothing left to project onto y, and we just get 0. The same thing happens if you do y first, and then x. The other case that's straightforward is when one of the subspaces is nested inside the other. For example, suppose one of our projections is to project onto the xy plane, and the other is to project onto the x-axis. One way we could do this is to first project the xy plane, then project the result onto the x-axis. What if we switch the order? Well, if you think about it, the x-axis is inside the xy plane. So if we project onto the x-axis, we're already projecting onto the xy plane. So if we try to project to the xy plane after this, that doesn't do anything. We're already there. So in the case of nested projections, whether you do the outer one or the inner one first, you get the result from just doing the inner projection. The third case is the more complex one. It's when the subspaces aren't nested, but do overlap. For example, maybe we project onto the xy plane, and also onto the xz plane. Those aren't nested, neither of them is wholly inside the other, but they do overlap because they both contain the x-axis. In this particular case, you can either project to the xy plane and then to the xz plane, or you can project to the xz plane and then the xy plane. And either way, the result you get is the same as if you had just projected to the x-axis, the overlapping part. Now, just having the spaces overlap is not sufficient for the projections to commute. It turns out that what's required is for the non-overlapping part of the subspaces to be orthogonal. In this case, the non-overlapping parts would be the y-axis from the xy plane and the z-axis from the xz plane. Those are perpendicular, and this is what I mean by orthogonally overlapping. So these projections do commute. So those are some examples where projections commute. As I said, when projection matrices commute, their combination is also a projection. That was true for the three cases we just looked at, but the general proof is pretty quick. If the combination PQ were a projection, then it should be idempotent. So we want to see if PQ squared is equal to PQ. If P and Q commute, then we can swap the order right here. And since P and Q are individually idempotent, that brings us back to where we started. So we've proved that the combination of commuting projections is itself a projection. To wrap this part up, let's see an example of when projections do not commute, and we'll look in 2D to make it easier to process. Consider projecting this vector onto the bottom line first, then projecting the result onto the top, versus projecting onto the top line first, then projecting the result onto the bottom. We get different ending vectors, so order matters in this case. Okay, that's multiplying projections. Another thing we could do is add them. I always find adding matrices to be sort of puzzling, since I usually think of matrices as linear transformations, and adding transformations is confusing. But because of the distributive law, the key is to think of it as performing two different transformations to the same starting vector, then adding the results. So for adding projections, think about taking some starting vector, then doing two different projections on it, then adding the results. Our starting question on adding projections is probably, does adding projections ever give something interesting? Basically, there are two cases when it does. First, adding projections can sometimes give us another projection. This happens when the two subspaces we're projecting onto are orthogonal and do not overlap. And second, adding projections can sometimes give us the identity matrix. This happens if we have enough orthogonal and non-overlapping projections to span the space. As an example of the first point, if we project this starting vector onto the x-axis and onto the y-axis, then add those up, the result is the same thing we would have gotten if we project onto the xy plane. You probably already have a decent intuition about this, because we're essentially just finding vector components, then adding them up. If we have enough projections onto enough different orthogonal, non-overlapping subspaces, then we've essentially found all of the components of the vector in some basis, so adding them back up gives us back the original vector. In the example, if we add in the projection onto the z-axis too, and add all three of these up, we just get back to our starting vector. In terms of matrices, that means that adding matrices that project in the x, y, and z directions will just give you the identity matrix. What if the projections are not orthogonal and non-overlapping? In that case, you don't necessarily get anything special. Here's an example. If we take this vector, then project onto each of these lines, then add up the results, we do not get anything in particular. The result won't be an orthogonal projection of the starting vector. Okay, here's one extra credit property of projection matrices that's actually more involved than I really want to get into, but maybe could come in handy for you at some point. It's that the trace of a projector is equal to its rank. We know that the rank of a projection tells you how many dimensions the surface that the transformation projects onto is. Recall that the trace of a matrix is what you get if you add up all the diagonal entries, like this. So how can the trace be the rank? Well, one more fact that you might know about the trace, that I won't prove here, is that the trace is always equal to the sum of the eigenvalues of the matrix. In our case, we know the eigenvalues are zeros and ones. How many zeros and ones? There will be a 0 for every dimension of the null space, and a 1 for every dimension of the surface we're projecting onto. Pause and think that through if you need to. But anyway, that means there's going to be an eigenvalue of 1 each for whatever the rank of the matrix is. When we add those up to take the trace, we'll get the rank of the matrix. Why did we look at that one if it's a bit obscure? Because it may come up again in a future video that will be relevant for statistics. so watch out for that. So, to recap all of that, we've got these properties for orthogonal projection matrices. They are idempotent, so that projecting twice is the same as projecting once. They are symmetric, which implies that dotting two projected vectors is the same as dotting one projected vector with one non-projected vector. They are less than full rank, so that projecting kills some dimensions. Relatedly, the eigenvalues of a projection are zeros in the null space and ones in the projection space. Projections commute if they are nested or orthogonally overlapping, and two orthogonal and non-overlapping projections will add to another projection, which if they span the whole space, will just give us the identity matrix. So that's it for this video. In the next episode, we'll look at the formulas for actually calculating a projection matrix based on the subspace you want to project onto. See you then, and thanks for watching.